Do you know which star is closest to Earth? If someone quickly answers Proxima Centauri, then the first thing this story needs to do is not move forward, but stop and correct the question itself. The star closest to Earth is the Sun. It is so familiar that people often see it as part of everyday life and forget that, in its true nature, it is also a star like countless other stars in the universe. Only by starting from that simple truth can we ask a more accurate question. Beyond the Sun, which star is closest to us? And why is it that a star called the closest still lies at a distance that human beings can hardly hope to cross? This question matters not because it leads us to a name, but because it forces us to recognize the limits of intuition. In ordinary life, what is near is usually something we can reach. Near often means something we can touch, something we can arrive at, something we can bring into direct experience. But in the universe, the word near no longer carries that meaning. On the scale between stars, the closest only means less far than the rest. It does not guarantee accessibility. It does not promise a journey within reach. It only reminds us that even Earth's nearest neighbor beyond the Sun is still separated from us by such a vast emptiness that all the familiar measures of human experience begin to fail. And that is exactly where this story begins. Not to exaggerate the mystery of the universe and not to turn distance into a hollow feeling of awe, but to face a very real paradox. In cosmic space, the closest can still mean almost impossible to reach. Once the question has been corrected, the real journey can begin. Why is the nearest star beyond the Sun still so far away from human beings?
Before we continue, Adam Stone would like to quietly thank you for staying here and listening this far. If gentle space and science stories like this bring you a peaceful pause before sleep, please consider subscribing to the channel and leaving a like to show your support. Your support helps Adam Stone continue creating slow, thoughtful stories about the universe, calm enough to stay with you through many nights to come.
Why is a star called the nearest and yet still far beyond human reach? The short answer is that our intuition was made for living on a planet, not for understanding the distances between stars. In everyday life, the human brain is very good at estimating distances that can be traveled, seen, or touched. But once we step beyond the scale of Earth and enter the scale between stars, that entire system of feeling and judgment begins to fail. On Earth, we are used to thinking in kilometers. A road of a few kilometers feels near. A trip of a few dozen kilometers is enough to move from one city to a nearby town. A journey of a few hundred kilometers already feels like something that requires preparation. When distance grows to a few thousand kilometers, we begin to think in hours of flight. From there, our sense of space forms naturally. Far is something that takes more time to reach, and near is something that still fits within the boundaries of lived experience. Even if we have never traveled across the whole world, we can still sense its size through maps, flights, oceans, continents, and familiar borders. But the scale of Earth, although large for a human being, is still extremely small when placed in an astronomical context. Traveling all the way around Earth is already a grand idea in ordinary life. Flying from one side of the planet to the other is enough to create the feeling of having crossed a very significant distance. That is why, when people first began to learn about the Moon, they naturally thought of it as an incredibly distant place. And by the standards of daily life, that reaction is completely understandable. The distance from Earth to the Moon is greater than almost every journey that fell within ordinary human travel experience through most of history. And yet on the scale of the universe, that distance is still so small that it is almost right next door. This is where intuition begins to slide away from reality. From Earth to the Moon, although the distance is large, human beings have still managed to cross it. From Earth to the Sun, the distance becomes so much greater that ordinary imagination begins to slow down, yet light still needs only a few minutes to cross it. That is still close enough for us to keep a vague feeling that the Sun belongs to the same familiar system as Earth. It is far, but not so far that it completely destroys our ability to imagine it. The solar system, although vast, is still a realm that human beings can divide into orbits, planets, probes, travel times, and fairly clear maps. But once we leave that range and begin speaking about the nearest star beyond the Sun, the language of daily life almost stops being useful. Not because the numbers become hard to read, but because lived experience no longer gives us any real foothold. A few light years may sound like a number that is not very large if we focus only on the word few. In everyday life, few means a small amount. A few minutes, a few days, a few kilometers, a few houses. The word suggests something moderate, close, not alarming. But when it is joined to the phrase light years, that little word becomes a trap of language. It makes the brain assume that this must still be something manageable. In truth, the moment those two words, light years, are added, the ordinary meaning of distance changes completely. A light year is not a unit created to make the universe sound poetic. It is a sign that the familiar units of human life are no longer large enough to contain reality. When we must use the distance that light travels in a year in order to describe the position of stars, that means kilometers have become too small, too awkward, too fragmented for the true scale involved. And here the central paradox of this story becomes clear. The nearest star beyond the Sun is not a place that is moderately far away. It is a place so distant that human beings had to invent an entirely different language in order to speak about it seriously. We often imagine that if something is the nearest neighbor, it must at least lie within the reach of imagination. But in astronomy, the nearest neighbor can still be separated from us by a desert of distance that is almost completely empty. Between Earth and the nearest star beyond the Sun, there are no familiar stopping points, no intermediate places shaped by ordinary life, no markers that help the brain divide the journey into parts it can truly feel. On Earth, a long trip is made up of shorter segments. There are airports, stations, harbors, cities, borders, resting places, schedules. In interstellar space, that kind of structure almost disappears. Distance is no longer a chain of places, it becomes an immense emptiness. That is why when people hear that Proxima Centauri is the nearest star beyond the Sun, many of them unconsciously understand the word near through the psychology of daily life. They hear in it the suggestion of a next destination, the next stop, a door at the end of the corridor, but the truth is far harsher than that. In the context of the universe, nearest does not mean near in the sense that human beings could reach it within a reasonable journey. It only means that if you had to choose one other star as the starting point for speaking about interstellar distance, this one is the least far away. That is all, nothing more. If we look at it through the intuition born on the ground beneath our feet, human beings are very likely to make a familiar mental mistake, taking a word we already know and carrying its old meaning into a world where it no longer fits. We do this with near, far, large, small, even with the word neighbor. But the universe is not bound by the language habits of human beings. A star can be our nearest neighbor and still lie beyond every practical journey our civilization can currently attempt. This is not a paradox invented to create drama. It is a foundational truth of astronomy, and if we do not accept that truth from the beginning, almost every attempt to imagine the stars afterward will slide into error. A more important lesson appears here as well, one deeper than the number itself. Intuition is not the enemy of understanding, but it has clear limits. It helps human beings survive, orient themselves, build daily life, and estimate space well enough within the boundaries of a planet. But when faced with the universe, intuition is no longer a trustworthy guide. It begins to pull us toward false comparisons, false feelings, and false conclusions. It makes us think that nearest means possible to reach soon. It makes us hear a few light years as though it were merely a slightly larger version of a long trip. In reality, it belongs to an entirely different order of distance, and that is why this section must stand at the beginning of this story as a hinge of thought. Before speaking about the name of the nearest star, before speaking about the planets around it, before speaking about the possibility of life or the dream of travel, we need to accept something more basic. The human mind was not made to feel the true scale of the universe correctly. Things that seem near in astronomy may still be so far away that no ordinary experience of life can represent them. Only when we understand that collapse of intuition are we truly ready to move forward. So if everyday feeling can no longer be trusted, what did human beings create in its place? If kilometers, flight times, and lived experience are no longer enough to help us imagine the distance between stars, then by what units and by what methods did we learn to measure the universe? When kilometers were no longer enough, what did human beings do to measure the universe? The answer is that we did not try to force that vast reality into the familiar scales of everyday life. Instead, we accepted that we had to change the very language of measurement itself. That was not a stylistic trick. It was a sign that the universe is so immense that the system of measurement used in daily life no longer fits. On Earth, the kilometer is a very natural unit. It is large enough for roads, cities, continents, and even the circumference of a planet. But once human beings began to look beyond Earth, especially within the solar system, the kilometer quickly became too small and too fragmented. Not because it was wrong, but because it turned enormous distances into strings of numbers so long that intuition could no longer hold on to them. That is why astronomy adopted a more compact unit for our local neighborhood, the astronomical unit. According to the definition accepted by the International Astronomical Union in 2012, one astronomical unit is exactly 149,597,870,700 meters, and it is close to the average distance between Earth and the Sun. The very fact that we need the astronomical unit already tells us something important. When people no longer want to say that Earth is nearly 150 million kilometers from the Sun every time they refer to the most familiar orbit in our lives, that means the old unit has started to become inconvenient. But the astronomical unit is truly useful only within the solar system. Beyond that, when we begin to speak about the stars, even the astronomical unit becomes too small. A nearby star such as Proxima Centauri, according to an illustration from the European Space Agency, lies at about 267,000 astronomical units. At that point, writing the distance in astronomical units does not make it easier to understand. It simply replaces one long string of numbers with another. So human beings had to take another step and use the light year. A light year is not a unit of time, but a unit of distance. The distance that light travels in a vacuum in 1 Julian year. The European Space Agency gives this value as about 9.5 trillion kilometers, while the International Astronomical Union gives the equivalent value as 9,460,730,472,580.8 kilometers, or about 63,241 astronomical units. That definition alone is enough to show the scale of the problem. When speaking about a star, human beings must borrow the fastest speed known in ordinary physics, let it run for an entire year, and only then do we arrive at a unit large enough to serve as a basic measure. But astronomy did not stop there. Alongside the light year, there is another unit that sounds stranger, even drier. yet is even more important in professional measurement, the parsec. This name did not come from poetic imagination, but from observational geometry. The European Space Agency explains it very clearly. A parsec is the distance at which an object has a parallax of 1 arc-second. 1 parsec equals 3.26 light-years, or about 3.09 times 10 to the power of 13 kilometers, or 206,265 astronomical units. In other words, a parsec is not a decorative name for a very large distance. It is a distance defined directly from the way a star appears to shift position as Earth moves around the Sun. At this point, something very important comes into view. Human beings do not measure the distance to a star by how bright or dim it looks, and not by guessing whether it appears large or small in the sky. That would lead to error almost immediately, because a dim star could be a faint star nearby, but it could also be a very bright star far away. A star that stands out to the eye is not necessarily closer than one that is hard to see. The European Space Agency stresses this when explaining the difference between apparent brightness and the true properties of stars. What the eye sees is not enough to reveal distance. To measure distance, astronomy must rely on structured observation, repeated over time, and open to verification. The most fundamental method in that shift is stellar parallax. Imagine Earth at two opposite positions in its orbit around the Sun, 6 months apart. When observing a relatively nearby star from those two positions, an astronomer will see the star appear to shift slightly against the more distant background stars. That shift does not happen because the star itself jumps from place to place in that short time. It happens because the observer's point of view has changed. The European Space Agency describes this as a triangle. The lines of sight from two observing positions and the star form a geometric shape that allows distance to be inferred. The nearer the star, the larger the apparent shift. The farther the star, the smaller that shift becomes. From that, an astonishingly compact formula appears. Distance in parsecs equals the inverse of the parallax angle, measured in arc-seconds, written as d equals 1 over p. This is one of the most beautiful moments in science. A vast distance between stars is finally connected to human understanding through a very simple triangle. But that simplicity hides a great difficulty. The parallax angles of stars are extremely small. The European Space Agency notes that angles smaller than about 0.01 arc-seconds are very difficult to measure accurately from the ground. So for stars farther away than about 100 parsecs, parallax measurements from Earth become severely limited. That means the challenge is not only a matter of geometry, but also of instrumental precision and the observing environment. Because of that limitation, the history of stellar measurement could not rely only on ground-based telescopes. The European Space Agency states that the Hipparcos satellite spent 3.5 years measuring stellar positions with unprecedented accuracy, allowing parallax measurements for about 120,000 stars out to roughly 500 light-years, or about 150 parsecs. Another experiment on the same mission, called Tycho, measured parallax for more than 1 million stars, though with lower precision. After that, Gaia pushed the revolution even farther. The European Space Agency describes Gaia as reaching micro-arc-second precision for many measurements of stellar position. What matters most here is not the names of the satellites, but what they represent. To measure the distance between stars, human beings had to learn how to detect and quantify changes so small that they lie almost beyond direct imagination. So when we hear units such as the astronomical unit, the light year, or the parsec, we should not treat them as words that merely make astronomy sound more elegant. They are evidence that reality is far larger than the frame of feeling provided by daily life. And when we hear about parallax, we should not think of it as only a technical detail. It marks the moment when human beings stopped estimating the universe through intuition and began measuring it through a method that can be repeated, tested, and corrected. In other words, the measures of the universe were not invented to make distance sound less dry. They were invented because without them, we would not only lack the language to describe the stars, but also the means to know whether what we are saying is true or false. And once we finally have that measuring system in hand, the next question becomes truly clear. Among all the stars beyond the Sun, which one is actually our nearest neighbor? What is the nearest star beyond the Sun, really? The answer is Proxima Centauri. But if we stop at the name alone, the listener can very easily form the wrong picture of the central subject of this story. Proxima Centauri is indeed the nearest star beyond the Sun, but it is not a large, bright lamp standing out in the sky, not a second sun waiting for humanity to reach it, and not an object that can be clearly seen with the naked eye, simply because it is closer than other stars. The National Aeronautics and Space Administration describes Proxima Centauri as a very faint, very small red dwarf star located a little more than 4 light-years from Earth, yet still invisible to the naked eye from the ground. The first thing that must be separated clearly is 3 layers of information that are often mixed together into one. Proxima Centauri is the nearest star beyond the Sun. Alpha Centauri is the nearest star system to us, and Proxima Centauri does not stand alone, but is the faintest member of that triple star system, alongside Alpha Centauri A and Alpha Centauri B. The European Space Agency states very clearly that the Sun's nearest neighbors are the 3 stars in the Alpha Centauri system, in which Proxima Centauri is the faint red dwarf closest to us, at about 4.24 light-years, while the pair Alpha Centauri A and Alpha Centauri B lie a little farther away, at about 4.37 light-years. That small difference in distance can easily make people think all 3 are almost the same point. But in astronomy, those small differences are enough to determine which one is truly the nearest neighbor. So when we say the nearest star beyond the Sun, the correct name is Proxima Centauri. But when we say the nearest star system, the correct term is the Alpha Centauri system. This story needs to preserve that distinction from the beginning, because with only one small confusion, the entire understanding of the central subject begins to drift away from the precision that science requires. But what is more interesting than its name is its physical nature. Proxima Centauri is a red dwarf, which means a type of star with low mass, a lower surface temperature than the Sun, and far less brightness. The National Aeronautics and Space Administration states that Proxima has a mass of only about 1/8 of the mass of the Sun, and because its average brightness is so low, even though it is the nearest star beyond the Sun, it still does not appear in the sky in the way human intuition would expect. It is not the nearest star and therefore more radiant than the others. On the contrary, its smallness and faintness are the very first things that must be understood correctly. This is a very important point for the tone of the entire story. If people look at Proxima Centauri through familiar imagination, they can very easily turn it into a grand symbol. The first doorway out of the solar system, the next destination of humanity, the neighboring star standing at the threshold of civilization. But the truth is far more modest than that. The European Space Agency notes that even with the sharp vision of the Hubble Space Telescope, Proxima Centauri still appears only as a point of light, an object that cannot be resolved into a clear stellar disk, as if that very image were reminding us of the enormous scale of the empty space around it. In other words, our nearest neighbor in the universe does not appear as a distinct place, but as a faint dot with almost nothing for human feeling to hold on to. That contrast is what makes Proxima Centauri such a special character. It is the nearest, but not the most striking. It is the nearest neighbor. but it does not create a feeling of nearness. It is mentioned again and again in stories about the future of interstellar travel, yet it is itself a small, dim star, almost invisible to the human eye. In the ordinary world, we tend to think that what is closer should appear more clearly, more brightly, and more vividly. Proxima Centauri completely breaks that habit. It reminds us that in astronomy, distance is only one part of the story. The nature of the object itself is what determines how it appears before our eyes. That is why the right way to introduce Proxima is not through exaggeration, but through restraint. This is not a finish line already opened before humanity. It is not a beacon of the future simply because it is closer than other stars by a fraction of a light year. First of all, Proxima Centauri is a very modest astronomical object, a small red dwarf star, faint, invisible to the naked eye, part of the nearest star system to us, and still more than 4 light years away. Only by accepting that less dramatic image can we begin to see it correctly as an object of science, rather than as a symbol onto which imagination wants to project its own meaning. At a deeper level, Proxima Centauri also reveals something worth thinking about in the way human beings tell stories about the universe itself. We are often drawn toward what is bright, large, and impressive. But the nearest star beyond the Sun does not belong to that kind of object. It was not chosen as our nearest neighbor because it is more beautiful, brighter, or more like the Sun. It is simply a little closer than the other stars in the surrounding region. Science does not build the hierarchy of the universe according to what moves human emotion the most. It simply records the facts, even when those facts are modest, quiet, and contrary to our first romantic expectations. And that is exactly how this part should come to a close. Proxima Centauri is not a legend waiting to be magnified. It is a real star, small, faint, the nearest beyond the Sun, and still more than 4 light years away. It belongs to the Alpha Centauri system, but it is not identical with the whole of Alpha Centauri. It lives in human imagination as the first milestone of interstellar distance, but before anything else it must be understood correctly in the precise language of astronomy. Once we know what Proxima is, and also clearly understand what it is not, the next question becomes truly important. How do human beings know with confidence that it is that far away from us? How do human beings know how far away a star is when no one can touch it and no one can travel there to measure it directly? The most important answer is this. Astronomy does not see distance the way the human eye sees whether a mountain is near or far. The distance to a star does not appear as a label already attached to the night sky. It is inferred from geometry, from motion, from extremely small differences in the apparent position of a star, and from measurements repeated long enough to separate the real signal from noise and error. That may sound abstract, but in fact it is very close to an ordinary human experience. If you look at a nearby object with your left eye and then switch to your right eye, the object seems to shift slightly against the background behind it. That shift does not happen because the object itself has moved, but because the position of the observer has changed. Astronomy uses exactly the same logic on a far larger scale. Earth moves around the Sun, so over the course of a year, we observe a star from different points along our orbit. Compared with the background of more distant stars, a nearby star shows a very small apparent shift. This effect is called stellar parallax. The European Space Agency describes it as the geometric foundation for inferring the distance to nearby stars. The nearer the star, the larger the parallax. The farther the star, the smaller the parallax. From that effect, human beings derived one of the most elegant formulas in astronomy. If distance is measured in parsecs and parallax angle is measured in arcseconds, then distance equals the inverse of parallax, written as d equals 1 over p. The formula is very short, but what it contains is enormous. It means that the distance to a star is not measured by rough estimation, and not by how bright or dim it seems, but by a geometric triangle that can be tested. A star at a distance of 1 parsec has a parallax of exactly 1 arc-second. As the parallax grows smaller, the distance increases accordingly. That is why a parsec is not only an unfamiliar unit of distance, but a unit born directly from the measuring method itself. But here a difficulty appears that ordinary intuition can hardly grasp at all. Those angles are incredibly small. The European Space Agency notes that stellar parallax angles are often so tiny that in many cases measurement from the ground is strongly limited by the atmosphere and by instrumental precision. Parallaxes smaller than about 0.01 arcseconds are very difficult to measure accurately with traditional ground-based observation. That means the problem is not that human beings do not know what must be measured. The problem is that the thing that must be measured is so small that it nearly disappears before ordinary perception. The universe does not reveal itself through large signs. It shifts only a little, very little, and then forces human beings to build instruments fine enough to detect that little shift. Parallax, however, is still not the whole story. When we observe a star over many years, its position in the sky changes not only because Earth changes position around the Sun, but also because the star itself is truly moving through space. The European Space Agency defines proper motion as the change in the angular position of a star over time, usually measured in arc-seconds per year. In other words, astronomy must not only detect the shift caused by a changing point of view, but also separate it from the shift caused by the star's own real motion. The European Space Agency also emphasizes that in order to distinguish parallax from true motion, astronomers need precise measurements extending over more than 1 year. This is the point where this story needs to pause long enough to see the real beauty of science. We often imagine that discovering the universe means moments of overwhelming astonishment, brilliant images, and discoveries that seem to arrive in a single glance. But for stellar distance, the truth is almost the opposite. No one looks once and immediately knows how far away a star is. What human beings have is a sequence of observations, repeated again and again at different times of the same object. And then mathematics is used to separate the different components of motion from one another. Here, the universe is not revealed by the grandeur of an image, but by the patience of measurement. That is why the history of measuring stars is the history of astrometry, the measurement of stellar positions with extremely high precision. The European Space Agency explains that the Hipparcos mission, operating in space at the end of the 20th century, spent 3.5 years measuring the positions of stars with unprecedented accuracy for its time. As a result, Hipparcos was able to measure the parallax of about 120,000 stars, reaching out to about 500 light-years, or nearly 150 parsecs. The Tycho experiment that accompanied it measured parallax for more than 1 million stars, though with lower precision. That was not only a technical achievement, it was the moment when modern astronomy began to build a trustworthy map of distances in the nearby stellar region around the Sun. After Hipparcos, Gaia pushed this work much farther. The European Space Agency describes Gaia as a mission that has carried out more than 3 trillion observations of about 2 billion stars and other objects, building a highly precise 3-dimensional map of positions, motions, brightness, temperatures, and many other properties of stars in the Milky Way. The National Aeronautics and Space Administration also notes that Gaia tracks stellar motion through the technique of parallax and repeated observations over time. For the astronomy of nearby stars, Gaia does not simply provide more data. It also makes the idea of our cosmic neighborhood less vague because the region near the Sun can now be described with a much denser and more uniform body of data than before. What is striking is that in such data, distance never stands alone. Position, parallax, proper motion, and sometimes radial velocity all come together to tell the true story of a star. A nearby star may show greater proper motion across the sky, not because it is faster, in an absolute sense, but because when it is closer, the same real speed produces a larger angular shift. The European Space Agency makes clear that proper motion is an angular quantity, and nearby stars often appear to move faster against the sky than distant stars when other conditions are similar. That reminds us that the night sky only appears motionless because a human lifetime is short and the human eye is crude. In precise data, the sky is a dynamical system that is constantly shifting. So when we say that Proxima Centauri is more than 4 light-years away, astronomy is not giving us a number in the manner of hearsay. That number is the output of a long-term system of measurement in which the geometry of Earth's orbit, stellar position tracking, observational sequences lasting many years, and the statistical treatment of error all work together. We do not see distance the way we see a road. We read it out of extremely small shifts, out of patterns of motion, and out of the consistency of data when the measurement is repeated over time. That is why astronomical distances, although they sound remote and abstract, can still be trustworthy in a very strict sense. They are not stories that are told, but distances that are measured. And it is exactly here that another truth begins to appear. Once we understand how stellar distance is derived through such rigorous methods, the listener no longer finds it easy to treat those numbers as dry symbols. Instead, they begin to carry weight. They are the result of thousands of tiny measurements, of many years of observation, of missions built solely to detect shifts so small that the human eye could never see them on its own. Once we understand how seriously that number was produced, the next question becomes much heavier. If the distance to the nearest star beyond the Sun is real, measured with such care, then how great is that distance in relation to human technology? Is the real problem that light takes more than 4 years to travel from Proxima Centauri to us? No. Light only gives us a standard for understanding distance. It does not give us a means of crossing it. When astronomy says that Proxima Centauri is about 4.2 to 4.25 light-years from Earth, it is describing the distance that light travels in more than 4 years, not the distance that a human spacecraft could cover in a similar amount of time. This is where distance begins to change its meaning. It is no longer just a number. It becomes a limit of technology. People very easily fall into a linguistic misunderstanding at this point. When they hear the phrase 4 light-years, many unconsciously hold on to the words 4 years and forget the decisive word that comes after them, light. In ordinary life, 4 years is a long period of time, but it still belongs to human experience. But 4 light-years is not a 4-year journey for human beings. It is a distance that only light can travel in 4 years. The moment that difference is ignored, the entire understanding of interstellar travel begins to drift off course. So how fast is the fastest spacecraft humanity has actually built? According to the National Aeronautics and Space Administration, Parker's solar probe has reached a speed of about 430,000 miles per hour, or roughly 692,000 kilometers per hour, faster than any human-made object ever recorded. That number sounds almost absurd when placed beside the habits of life on Earth. It is fast enough to go from New York to Tokyo in less than a minute. But even that record speed does not make the interstellar problem easy, because humanity's speed record within the solar system is still extremely small when placed against the distances between stars. At this point, a cold truth begins to appear. If we take the distance to Proxima Centauri, which the National Aeronautics and Space Administration gives us about 40,208,000,000,000 kilometers and compare it to the record speed of about 692,000 kilometers per hour reached by Parker Solar Probe, the division gives a journey of about 6,600 years. And even that is only an idealized comparison in pure arithmetic. It assumes that a spacecraft could maintain that peak speed across interstellar space, which current technology cannot do. In other words, even if we use the fastest speed humanity has ever reached as a way to imagine the trip, the result already lies far beyond the time scale of any ordinary mission of civilization. But even that comparison is still too generous to present technology, because the record speed of Parker Solar Probe is a peak speed reached when it dives deep into the Sun's gravitational field during close passes, not a sustainable cruising speed for an interstellar voyage. This is a very important physical distinction. Reaching a high speed along one part of an orbit in the solar system does not mean that we possess a technology capable of carrying a spacecraft, fuel, communication systems, and scientific payloads for thousands of years through interstellar space at anything like the same speed. So if we look instead at spacecraft that are actually leaving the solar system on escape trajectories, the picture becomes much harsher. Voyager 1 gives us a more realistic standard. The National Aeronautics and Space Administration states that Voyager 1 is now leaving the solar system at about 17 kilometers per second, or about 3.6 astronomical units per year. If we take the distance to Proxima Centauri as about 268,770 astronomical units and divide it by that escape speed, the travel time comes out to roughly 74,000 to 75,000 years. This is no longer the timescale of a spacecraft designed by one generation and then followed to its destination by that same generation. It is longer than the entire span of most written civilization on Earth. And that is before we even begin to deal with slowing down in order to truly arrive. There is another detail here that is often forgotten. Reaching a star is not simply a matter of racing toward its coordinates. A real scientific mission would also require communication, power, long-term durability of instruments, protection against radiation, and, if the goal is to study that star system in a meaningful way, a solution to the problem of slowing down on arrival. An object that flies past at enormous speed is not the same thing as a mission capable of sustained observation. That is why interstellar distance is not merely a problem of engines. It is a combined problem of energy, materials, time, and the total ability to keep a technological system functioning across timescales longer than the lifetime of any space program that currently exists. The advanced studies on interstellar exploration produced by the National Aeronautics and Space Administration exist precisely because of that limit, not because the problem is close to being solved. Compared with that entire picture, what matters is not one single number, but the enormous gap between the speed of light and the speed that current technology can actually achieve. Light takes only about 4.24 to 4.25 years to travel from Proxima Centauri to Earth. By contrast, if we use the peak speed of Parker Solar Probe as an idealized way of imagining the journey, the trip still comes out to about 6,600 years. And if we use the standard of a spacecraft that is truly escaping the solar system, such as Voyager 1, the travel time becomes roughly 75,000 years. Whichever reference point we choose, the central meaning does not change. Between the standard speed of light and the speed that present-day technology can use for real exploration, there is still a vast abyss. Interstellar distance does not defeat humanity only because it is large. It defeats humanity because every means we currently possess is far too slow compared with the very standard used to define that distance in the first place. And that is the central point of this story. The problem is not that we do not know where Proxima Centauri is. We know quite well where it is, how far away it is, and why it is the nearest neighbor beyond the Sun. The problem is that knowing the way does not mean being able to go there. Light can cross that emptiness in a little over 4 years, while human technology still remains trapped at a level so much slower that such a journey would either stretch across tens of thousands of years by the standard of real escape trajectory spacecraft, or remain only an idealized comparison if we rely on peak speeds achieved within the solar system. That difference is what turns nearest into almost impossible to reach. And yet from that very point, another paradox begins to open. Even though humanity knows it cannot yet touch Proxima Centauri, it still keeps turning telescopes toward it. Why? Because around that small, dim, and distant star there may be other worlds, and that possibility alone is enough to turn Proxima from a number that measures distance into a very special scientific target. What is there around the nearest star beyond the Sun? The answer makes Proxima Centauri more than just a marker of distance. Around that small and faint red dwarf star, there is not only emptiness, at the very least, we already know of Proxima b as an exoplanet orbiting it, and in the popular descriptions of the National Aeronautics and Space Administration, it is the nearest known exoplanetary neighbor to us. That alone changes the entire tone of the story. Proxima is no longer only the nearest star beyond the Sun. It is also a star system with worlds close enough for human beings to ask serious questions about the conditions of planets beyond the solar system. But this needs to be said honestly from the very beginning. The most compelling part of this story is not the promise of life, but the scientific value of an object that is very near. The National Aeronautics and Space Administration describes Proxima b as a super-Earth, orbiting an M-type star with a mass of about 1.055 times the mass of Earth, an estimated radius of about 1.02 times the radius of Earth, an orbital distance of about 0.0485 astronomical units from its parent star, and an orbital period of only about 11.2 days. When a planet roughly the size of Earth exists in the nearest star system to us, it automatically becomes a special natural laboratory, not because it is certainly like Earth, but because it is the nearest target for testing basic questions about rocky planets around red dwarf stars. That short orbit is exactly what makes Proxima b both fascinating and difficult to understand. If we placed it in the solar system, a year, only 11.2 days long, would sound far too close to its parent star to be associated with familiar surface conditions. But Proxima Centauri is not the Sun. It is a red dwarf star with much lower brightness, so the region receiving what might be considered a milder level of energy lies much closer to the star than Earth does to the Sun. That is why the European Southern Observatory announced in 2016 that Proxima b lies in a region where liquid water could exist on the surface under certain conditions. However, lying in the habitable zone does not mean being habitable. It only means that, judged by the amount of energy it receives from its star, this planet is worth deeper study. This is also the moment when this story must remain disciplined in the way it speaks. Proxima b should not be called a second Earth, because the similarities to Earth stop rather quickly. The National Aeronautics and Space Administration points out that Proxima b is much closer to its star than Earth is to the Sun, and because it orbits so close, it is likely tidally locked. That means one side of the planet may always face the star, while the other side remains in permanent darkness, instead of having a cycle of day and night like Earth. That detail alone is enough to show that this is not a simple version of our world, but a very different kind of planet, with a very different climate system and environment. So why does a planet like this still exert such a strong pull on our curiosity? Because it forces science to work in the region where hope and discipline meet. On one hand, Proxima b is close enough to become a priority target for climate models, radial velocity measurements, and, in the longer term, more refined attempts at direct observation. On the other hand, it orbits a red dwarf star well known for strong activity. The National Aeronautics and Space Administration notes that Proxima Centauri is an active star with flares and a radiation environment that could strongly affect the atmosphere of a nearby planet. In other words, Proxima b is compelling, not because it gives us an easy answer, but because it poses a difficult test for every simple idea about life around red dwarf stars. If we look more broadly, the Proxima system may contain more than one planet worth mentioning. The National Aeronautics and Space Administration now also has an entry for Proxima Centauri d, describing it as a much smaller rocky planet with a mass of about 0.26 times the mass of Earth, an orbital period of about 5.1 days, and an orbital distance of about 0.0288 astronomical units. The European Southern Observatory also announced in 2022 the detection of Proxima d as a planetary signal very close to its star, orbiting between the star and the habitable zone. That does not mean the Proxima system is fully understood. On the contrary, it shows that even in the nearest star system, we are still moving forward step by step, carefully distinguishing between a planet that is strongly supported, a promising signal, and ideas that still require more data. That caution is exactly what makes science trustworthy. Even so, throughout the whole system, Proxima b remains the natural center of public curiosity and popular science. The reason is not hard to understand. It is close, it has a mass on the scale of Earth, and it orbits the nearest star beyond the Sun. In many descriptions from the National Aeronautics and Space Administration, it is presented as the nearest exoplanet known to humanity. That combination alone is enough to make it almost impossible to ignore in any serious story about worlds beyond the solar system. But the value of Proxima b does not lie in how quickly it lets us dream. Its value lies in the way it forces us to ask the right questions. How would a rocky planet close to a red dwarf star retain an atmosphere, balance heat, and sustain conditions stable enough for a long-lasting surface environment? This is where the attraction of Proxima b reveals itself in its most mature form. It is not compelling because it has proved the existence of life. At present, we have no evidence of life on Proxima b. It is not compelling because its surface has been photographed or because its atmosphere has been established with certainty in the way the public often imagines. Its real attraction lies in the fact that it is the nearest problem that exoplanet science can pose around another star. If the very nearest neighbor beyond the Sun already has a rocky planet orbiting a highly active red dwarf every 11.2 days, then what conditions would be enough for such a world to endure over long periods of time? That question is concrete, modest, and precisely for that reason more valuable than any sensational promise. And that is why this section needs to stop at exactly the right point. There really are planets around Proxima Centauri, and Proxima b is the greatest intellectual reward in the story so far. The nearest world beyond the solar system that we know of, orbiting very close to a small and violent red dwarf star, near enough to become a special scientific target, yet still offering no excuse for easy conclusions about life. The more fascinating it becomes, the more it forces us to face a harder question. Does being near in astronomical terms truly mean being easy to live on, or does it only mean being a little less far away in a universe that remains profoundly harsh? Does being the nearest also mean being the most friendly? The answer is no. A star system like Proxima Centauri attracts scientific attention not because it is gentle, but because it places us exactly where hope and limitation collide. Proxima is a red dwarf star, a type of star that is small, dim, and extremely common in the Milky Way. Precisely because it is small and dim, the planets close to it become easier to study. But for that same reason, any planet that wants to receive a level of energy that is just right must orbit very close to its parent star. The European Space Agency explains clearly that the region where liquid water may exist around a red dwarf lies much closer to the star than the comparable region around the Sun, while the National Aeronautics and Space Administration emphasizes that red dwarf stars are the most common type of star in the galaxy, and that their small size makes the study of orbiting planets especially compelling. That is exactly what makes red dwarfs both attractive and troublesome. On paper, a planet orbiting close to a red dwarf may lie in a region where liquid water could, in theory, exist on its surface. But in reality, being so close to its parent star places that planet in an energy environment far harsher than anything familiar from Earth. The National Aeronautics and Space Administration explains that planets in the habitable zone of a red dwarf, because they must orbit so near the star, may be exposed to extremely intense X-ray and ultraviolet radiation, in some cases reaching hundreds of thousands of times the intensity that Earth receives from the Sun when the red dwarf is highly active. In other words, the right temperature range does not mean the right living environment. In the case of Proxima b, that pressure becomes much clearer. The National Aeronautics and Space Administration describes this planet as orbiting its parent star in only about 11.2 days at a distance of 0.0485 astronomical units, which means it is far closer to its star than Earth is to the Sun. Such a short orbit makes Proxima b an extremely valuable target for observation, because its orbital signal repeats quickly and does not require the long waiting times needed for Earth-like planets around Sun-like stars. But that same closeness also means that it must exist under the direct influence of a red dwarf star that is far from calm. In that sense, nearness is an advantage for scientific observation, not a sign that the planet itself is more gentle. Proxima Centauri is not a quiet lamp in the dark. The astrobiology research of the National Aeronautics and Space Administration records that Everscope once observed a flare from Proxima so strong that the star, normally invisible to the naked eye, became temporarily visible. That detail is memorable because it shows that the true nature of the nearest star beyond the Sun is not gentle nearness, but a kind of violent activity capable of suddenly pouring huge amounts of energy into the surrounding space. A red dwarf like this may be smaller than the Sun, but smaller does not mean kinder. In some cases, it may make the environment around nearby planets more hostile, because those planets do not enjoy a wide, safe distance like the one Earth has from the Sun. This is where the atmosphere problem becomes especially serious. The National Aeronautics and Space Administration makes it clear that the fact that Proxima b lies in the habitable zone does not mean that it is actually habitable. In models that use an Earth-like atmosphere as the standard of comparison, intense radiation and frequent flares from Proxima Centauri could make it very difficult for the planet to preserve an atmosphere like Earth's at its present orbit. Another study from the astrobiology program of the National Aeronautics and Space Administration goes even further, stating that within Proxima's habitable zone, Proxima b may be exposed to high-energy ultraviolet bursts hundreds of times stronger than what Earth experiences, enough to strip away not only hydrogen, but over time oxygen and nitrogen as well. In that model, the rate of atmospheric erosion could be about 10,000 times greater than on Earth. This is not proof that Proxima b is certainly bare and lifeless, but it is a very strong reminder that the nearest can still come with an environment far too harsh to maintain stable conditions for life as we know it. Then there is another problem that is often rushed through in popular science: tidal locking. Illustrations and descriptions from the National Aeronautics and Space Administration suggest that Proxima b is likely tidally locked, meaning that one side of the planet may almost always face the star, while the other side remains in permanent darkness. That does not automatically rule out the possibility of stable climate regions, but it makes the climate problem far more complicated than it is on Earth. When a planet has no familiar cycle of day and night, the entire question of winds, clouds, heat distribution, ice, oceans, and atmospheric stability has to be reconsidered from the beginning. That is why simply hearing that a planet lies in the habitable zone and jumping straight to the conclusion that it could support life means skipping over almost the entire hardest part of the problem. Even the age of a red dwarf does not guarantee the kind of calm we might hope for. A study from the National Aeronautics and Space Administration on Barnard's star, an old and relatively nearby red dwarf, shows that even long-lived red dwarfs can still unleash flares powerful enough to threaten the atmospheres of rocky planets orbiting in the habitable zone. The National Aeronautics and Space Administration concludes that planets in the traditional habitable zone around red dwarfs may fail to retain their atmospheres if such flares continue over long enough periods of time. Barnard's star is not Proxima, but the meaning of that result is highly important for how we think about red dwarfs in general. Great age does not automatically turn them into gentle environments for nearby worlds. From the observational point of view, this creates another interesting paradox. Red dwarf stars are extremely attractive targets because the small size of the star and the short orbital period of the planet make planetary signals easier to detect and follow, but the intense activity of the star can also contaminate the observational problem itself. When a star frequently flares, emits X-rays, ultraviolet radiation, and changes in brightness, scientists must work much more carefully to separate what belongs to the planet, what belongs to the atmosphere, and what is simply the instability of the star itself. In other words, red dwarfs give us nearby targets and rich data, but they do not give us easy answers. This is a very important inference from the two sides of the problem described by the National Aeronautics and Space Administration and the European Space Agency. Such systems are easier to access observationally, yet harder to interpret in terms of environmental conditions for life. That is why this part of the story must keep an almost ethical attitude toward knowledge. Serious science does not move from a few exciting facts to one enormous conclusion. It does not turn the existence of a nearby rocky planet into the claim that we have found the next place to settle. It does not turn lying in the habitable zone into proof of life. What we have at Proxima today is a picture filled with both promise and warning, a very nearby star, very interesting planets, but also a radiation environment, flare activity, and climate dynamics complicated enough that every optimistic conclusion must slow down. When Proxima is viewed in that way, an important illusion collapses on its own. The nearest does not mean the most friendly. The nearest also does not mean the natural next destination of humanity. It only means that this is the first place our curiosity encounters when it steps beyond the solar system, and the first place that forces us to restrain romantic imagination in order to preserve accuracy. Once we understand that Proxima is not a paradise waiting for us, the story can finally turn back toward humanity with a deeper question. Why do we still want to go to such a place, even knowing that it is not easy to live on, not easy to reach, and does not promise any simple reward? Why do human beings still want to travel to the stars, even knowing that the distance to Proxima Centauri is almost beyond our present ability? The answer does not lie in innocence before difficulty, but in the fact that human curiosity always reaches farther than the technology we currently possess. And yet, the moment we think seriously about such a journey, we realize that this is no longer merely the problem of building a stronger engine. It becomes the problem of an entire civilization, where the energy will come from, how the spacecraft will survive, how human beings will endure, and who will still carry responsibility for the mission when those who began it are long gone. The first lesson Proxima forces us to learn is this: interstellar distance does not challenge only speed, it also challenges the very way a mission is organized. In an overview by the National Aeronautics and Space Administration on the prospects of interstellar propulsion, The systems of a spacecraft would not only have to operate almost entirely on their own because communication delays would be measured in years, but would also need to detect faults, recover from them, navigate, and sustain themselves in a hostile environment for extraordinarily long periods of time. The National Aeronautics and Space Administration also emphasizes that maintaining mission reliability and continuous support across many generations would require an entirely different approach to spacecraft design, systems engineering, and mission operations. In other words, a journey to Proxima is not simply a matter of going farther. It is a matter of sustaining a technical will for longer than any space program humanity has ever managed. Then there is another layer of difficulty that intuition often overlooks: dust. Within the solar system, tiny dust grains can already damage spacecraft. The European Space Agency describes dust particles moving at a few kilometers per second as being able to erode surfaces much like sandblasting against important panels. For a hypothetical interstellar probe traveling at a significant fraction of the speed of light, the problem becomes far more severe. A technical roadmap from the National Aeronautics and Space Administration for interstellar flight estimates that across a journey of about 4 light years, even dust grains on the scale of microns could collide with non-negligible probability, while larger particles on the scale of millimeters could cause catastrophic local damage or even destroy an extremely light spacecraft if encountered. For that reason, the shape of the craft, its cross-sectional area, its direction of travel, the shielding material at its front, and the level of redundancy in its electronics all become matters of survival. And even if the dust problem were solved, the spacecraft would still have to pass through a radiation environment that human beings were never born to endure. The National Aeronautics and Space Administration emphasizes that our bodies and minds evolved on Earth, whereas outside the magnetic field and atmosphere that protect this planet, astronauts must face galactic cosmic radiation, energetic particle events from the Sun, microgravity, isolation, and prolonged confinement in a closed environment. In material related to the architecture for Moon to Mars, the National Aeronautics and Space Administration states that shielding can be effective against solar particle events, but can reduce the dose from galactic cosmic radiation by only about 7 to 15%. The European Space Agency also makes clear that ionizing radiation in deep space creates serious health risks such as cancer, cardiovascular effects, and cataracts. That means an interstellar journey with human beings on board would not only require enormous energy, it would also require a level of life protection that even missions to Mars are only beginning to learn how to approach, and radiation is still not the whole problem. The National Aeronautics and Space Administration also points out that long-duration spaceflight causes bones to lose density, muscles to weaken, the cardiovascular system to lose efficiency, and the immune system to change, while prolonged isolation and confinement create a very particular kind of psychological stress. One document on human factors from the National Aeronautics and Space Administration describes long missions as environments that separate people from family, confine them in narrow living spaces for months or years, deprive them of privacy, and burden them with group tension. Even for missions lasting only a few months or a few years within the solar system, these risks are already real. If the problem is extended to centuries or more, then we are no longer speaking about the endurance of astronauts. We are speaking about whether a closed social ecosystem could continue to exist across time at all. That is why, when interstellar travel is discussed, what is truly being tested is not only physics, but also the concept of responsibility. A mission lasting longer than a human lifetime cannot be imagined according to the familiar model. One group designs it, one group launches it, and then that same generation reads the data that comes back. At a distance such as Proxima, the National Aeronautics and Space Administration itself has treated continuous support across many generations as a foundational challenge for an interstellar mission. At that point, the question is no longer simply whether we can go. The question becomes who has the right to begin a project whose consequences, costs, and meaning will mostly be handed over to people not yet born. That is the moment when physical distance begins to turn into a problem of ethics and civilization. For that reason, serious discussion usually dares to speak only of frameworks for thought, not of ready-made solutions. One direction is the idea of world ships, or multi-generational ships, described by the Ames Research Center of the National Aeronautics and Space Administration as enormous self-sustaining habitats in which many generations of human beings would live and die during a journey lasting centuries before their descendants finally reach the destination. The value of this idea lies in the way it forces us to think about society, biology, education, law, and the meaning of being born on a spacecraft instead of on a planet. But that very description is also enough to show that this is not yet a technology waiting to be assembled. It is a thought experiment about the limits of civilization. Another direction is to reduce the target to an extreme degree, not to carry human beings, not to carry a large laboratory, but to carry ultralight probes. Studies published by the National Aeronautics and Space Administration on ideas such as breakthrough starshot describe tiny star chips, only 2 to 3 grams in mass, attached to laser-driven sails, with the ambition of reaching about 20% of the speed of light, so that they could pass through the region of Proxima in a few decades. But even on the research pages of the National Aeronautics and Space Administration, the difficulties appear very clearly. The mass available for power, observation, and communication systems must be extraordinarily small, in some proposals measured even in milligrams, far below any practical power system that currently exists. That is a sign that the boldest ideas today are still at the conceptual study stage, not at the stage of ready solutions. Even in the most optimistic scenario for ultrafast probes, the problem is still far from simple. One study from the National Aeronautics and Space Administration on interstellar propulsion notes that a probe passing through the destination system at about 10% of the speed of light, if it has no braking mechanism, would have only about 1 hour in the immediate region near the target to collect high-value data. That means shortening the travel time creates another limit. You arrive very quickly, but you have almost no time to remain there. And if slowing down is required, then the entire problem of energy, mass, and mission structure expands into yet another higher level of difficulty. So between multi-generational ships and laser sail probes, we do not see two clear paths about to open. We see more clearly two extreme forms of trade-off that interstellar travel forces humanity to confront. That is why this section needs to end with a very sober realization. The longing for interstellar travel is real, and it is not foolish. It grows out of the same impulse that once drove human beings beyond familiar continents, across oceans, toward the construction of telescopes, and toward sending spacecraft out of the solar system. But when it is placed against the distance to Proxima Centauri, that longing is no longer a simple adventure. It becomes a test of energy, materials, medicine, automation, social organization, and the ethics of commitments that must endure across generations. The more seriously we think about going to Proxima, the more clearly we begin to see something more surprising. Perhaps the greatest value of the nearest star does not lie in the journey it inspires, but in the way it forces us to understand more deeply just how special Earth remains in the real life of human beings. What happens to the way human beings see Earth once they have measured the distance to Proxima Centauri? The first thing that happens is not a feeling of pessimism, but a correction of scale. When the National Aeronautics and Space Administration describes Proxima as the nearest star beyond the Sun at about 4.24 light-years away, And the European Space Agency reminds us that even the nearest star is still about 40 trillion kilometers from us. That number does not merely describe a distant destination. It forces us to realize that Earth's surrounding region, in the interstellar sense, is almost an enormous emptiness. On that map, neighbor is no longer the idea of a short journey, but the name we give to an abyss that light itself needs more than 4 years to cross. For that reason, studying Proxima does not make Earth smaller, in the trivial sense that we are only a meaningless speck of dust. On the contrary, it makes Earth stand out more clearly as a nearby exception. The National Aeronautics and Space Administration describes Earth as the only place we know to host life, or, more directly, the only place where we know living organisms actually exist. In a universe where even the nearest star is separated from us by a distance that is almost impossible to cross, that fact becomes heavier. Earth is not precious because it sits at the center of the universe. Earth is precious because, up to this moment, it is the only place where life is not a hypothesis, but a direct experience. The distance to Proxima also changes another mental habit of humanity, the habit of judging the world by emotional impressions of near and far. On Earth, what is near is usually what is easy to approach, easy to affect, easy to imagine. But when astronomy forces us to use parallax, parsecs, and observations repeated over many years just to know where a star is, it is sending a very quiet message. Reality has no obligation to fit our intuition. The European Space Agency explains that even for the nearest stars, annual parallax shifts are extremely small and require instruments of very high precision. For that reason, building a map of stellar distances is the result of persistent observation more than immediate feeling. Here, the value of science begins to appear in a way very different from popular imagination. The universe does not open itself to humanity first through grand declarations. It opens itself through tiny measurements, through shrinking margins of error, through the willingness to accept that we do not yet know enough. The European Space Agency states that Gaia has carried out more than 3 trillion observations of about 2 billion stars and other objects in order to build a highly precise three-dimensional map of the Milky Way. That scale alone is enough to express the spirit of modern science, not to look harder in order to see more, but to measure more accurately in order to say less that is wrong. Seen in that way, Proxima Centauri becomes more of a mirror than a promise. It reflects back the true limits of humanity. We can know that a star lies more than 4 light-years away, identify it as the nearest neighbor beyond the Sun, and even detect planets orbiting it. But knowing is not the same as reaching, and discovering is not the same as possessing. The National Aeronautics and Space Administration describes Proxima b as a very nearby exoplanet, with an orbital period of about 11.2 days around a red dwarf star, while also emphasizing that the search for life beyond Earth has only truly begun, and that what remains unknown is still enough to fill many books. Distance, therefore, is not only a technical obstacle, it is also a reminder of intellectual humility. That does not make the story of other worlds any less beautiful. It simply makes that beauty more mature. In much popular discussion, people want to turn every Earth-sized or Earth-like planet into a second copy of home. But the National Aeronautics and Space Administration maintains a more careful attitude. Earth remains the only place where we know life exists, while the search for life elsewhere is still an open scientific program, not a closed conclusion. Set beside Proxima, the meaning of distance changes completely. What is very far away is no longer a place for rushing into fantasy, but a place that teaches us to slow down before limited data. So studying the nearest star does not lead us away from Earth in any simple emotional sense. It leads us back here with different eyes. The National Aeronautics and Space Administration has written that the more we learn about out there, the more we realize how special in here really is. That is not a slogan, but a very practical conclusion when the facts are placed side by side. On one side, a distance of more than 4 light-years that only light can cross in that span. On the other side, a planet with an atmosphere, water, active geology, and confirmed life. Studying Proxima does not reduce the value of Earth. It makes that value less abstract. At a deeper level, this is also a lesson in the ethics of scientific speech. When data are still limited, serious science does not jump from a few promising signals to vast conclusions. The European Space Agency uses parallax to measure distance. Gaia repeats observations trillions of times. The National Aeronautics and Space Administration states clearly that the search for life is still in its early stages. All of these point toward one shared virtue, moving more slowly than the desire to conclude. In an age that very easily turns the universe into a stage for grand claims, the actual way astronomy works teaches the opposite lesson. The greater the distances before us, the more precise, cautious, and honest we must become about what we do not yet know. And perhaps that is the greatest gift Proxima Centauri offers to human understanding. It does not give us a short road to the stars. It gives us the true scale of the world we live in. In that picture, Earth is no longer a place so familiar that it can be taken for granted. It appears instead as something very rare, near enough for us to belong to it, fragile enough to need protection, and special enough that every story about the stars finally returns to the same old question humanity still cannot leave behind. If we cannot yet travel to those worlds, then what is the right thing for us to do today, with the only home we know for certain is alive? If we cannot yet reach Proxima Centauri, then what is the right thing for humanity to do today? The answer is not to promise that a voyage is just around the corner, and not to build visions larger than our actual capabilities. What we can truly do today is observe better, measure more precisely, model more carefully, and speak more honestly about what the data really allow. That may sound less dramatic than a promise of reaching the stars, but it is exactly along that less dramatic path that science truly moves forward. Over the past many years, the greatest progress in astronomy has not been in shortening the distance to the stars, but in making our picture of them less blurred. The European Space Agency states that Gaia has carried out more than 3 trillion observations of about 2 billion stars and other objects in the Milky Way and beyond, creating an extraordinarily precise 3-dimensional map of their motions, brightness, temperatures, and compositions. What matters is not only that this produced an immense body of data, but that it changed the quality of every question that comes after it. If we want to know where a nearby star is, how it moves, what type of star it is, and why it is worth following, then we must first have a map good enough to prevent intuition from being mistaken for reality. At the same time, the study of exoplanets has also advanced in a very clear direction, not only by finding more planets, but by learning how to read their atmospheres from light. The National Aeronautics and Space Administration explains that the James Webb Space Telescope can use transmission spectroscopy to compare the light of a star before and after it passes through a planet's atmosphere. The portions of light that are missing at different wavelengths reveal which atoms and molecules are present. In the case of WASP-39b, the James Webb Space Telescope showed that the planet's atmosphere contains notable molecules, and the National Aeronautics and Space Administration stated that this was the first time sulfur dioxide and carbon dioxide had been detected in the atmosphere of an exoplanet, as well as the first evidence of photochemistry in this kind of atmosphere. Results like these do not tell us that life has been found. They tell us that human beings have begun to read the chemistry of worlds beyond the solar system through real spectroscopic data. But observation alone is still not enough. Good data only become meaningful when they are joined with models good enough to interpret them. The National Aeronautics and Space Administration makes clear that characterizing exoplanets with the James Webb Space Telescope requires detailed atmospheric models, spectral retrieval techniques, and new ways of dealing with clouds, haze, and many other sources of uncertainty. In other words, science today is not only about collecting more light, but also about learning not to misunderstand that light. An atmospheric spectrum does not tell the whole story by itself. Human beings must use radiative physics, atmospheric chemistry, and statistics to infer what may be present and then gradually eliminate what does not fit. It is that process that makes understanding move slowly but move forward in a real way. That is also why the study of red dwarf stars such as Proxima Centauri remains especially important. The National Aeronautics and Space Administration emphasizes that red dwarfs have habitable zones that are very narrow and very close to the star, which means that planets within those zones may be subjected to X-ray and ultraviolet radiation hundreds of thousands of times stronger than what Earth receives from the Sun in some highly active red dwarf environments. At the same time, the National Aeronautics and Space Administration also notes that Earth-sized worlds around Sun-like stars are much harder to detect, so most of the small planets we study today are found around red dwarfs instead. That means an important part of current science is not declaring that a new place for settlement has been found, but patiently answering a harder question. Can planets close to red dwarf stars truly retain their atmospheres, retain water, or preserve climate stability over long periods of time? One especially memorable example of the right scientific attitude is this. New data sometimes do not open up a broader vision, but instead narrow what we are allowed to say. In recent updates from the National Aeronautics and Space Administration, data from the James Webb Space Telescope have not yet shown clear evidence for an Earth-like atmosphere on TRAPPIST-1d, while research continues both on this planet itself and on its sibling worlds. This is a kind of progress that is very important, yet often does not sound spectacular. We do not receive better news, but a picture that is more accurate, narrower, and less romantic. In science, that kind of progress is often more valuable than a beautiful conclusion reached too early. Beyond understanding individual planets, humanity today can also do something else that is just as durable: build statistics large enough that we no longer have to see each exoplanet as an isolated miracle. The National Aeronautics and Space Administration states that its exoplanet catalogue, which is updated continuously, now contains more than 6,000 confirmed exoplanet entries. That number does not automatically bring us closer to life beyond Earth, but it allows science to move from the stage of asking whether such planets exist at all to the stage of asking how they are distributed, which types are common, which orbits are frequent, and which kinds of stars are most often associated with which kinds of planets. Once the sample becomes large enough, each individual discovery becomes less exaggerated, and the overall picture begins to grow more trustworthy. Even preparations for the near future carry that same spirit. The National Aeronautics and Space Administration has published the Target Star Catalogue as a list of promising stars for future missions, such as the Habitable Worlds Observatory. According to the National Aeronautics and Space Administration, this observatory will be the first space telescope built specifically to find and directly observe Earth-like exoplanets, and at the same time to study them for possible signs of life. Yet the National Aeronautics and Space Administration also emphasizes that this target list will continue to change as those stars are studied further. That detail is valuable because it shows that serious science always leaves room to revise itself. Even at the stage of preparing the largest instruments of the future, people still work with provisional lists, updated criteria, and an attitude that does not treat any assumption as permanent. So what we can truly do today is not turn Proxima into a nearby promise, but turn our lack of knowledge into questions that can be measured. We measure distance better, we read spectra better, we model atmospheres more carefully, we build larger statistical studies of exoplanets, we gradually learn the true environments of red dwarf stars instead of projecting hasty hopes onto them, and just as importantly, we learn to speak in the right scale about what we know. If something is only a sign, we call it a sign. If something is only a possibility, we call it a possibility. If there is no evidence yet, we say plainly that there is no evidence yet. Perhaps this is where the story most needs to test itself in order not to fall into the kind of dishonesty that so easily appears in popular science content. Do not exaggerate a planet into a second Earth simply because it is close to Earth in size. Do not turn lying in the habitable zone into being able to support life. Do not turn a suggestive spectrum into proof of an Earth-like atmosphere. Do not turn future instruments that are being prepared into a claim that humanity is about to find life. The greatest value of science content is not to overwhelm the listener for a few minutes, but to help them understand reality a little more correctly, and to understand it correctly for longer than the first moment of excitement. After everything that has been covered, distance, measurement, technological limits, the attraction of nearby planets, and the harshness of red dwarf stars, the story is now mature enough to close. Because once every glittering surface has been stripped away, what remains is not only the name of the nearest star beyond the Sun, but a deeper lesson about how human beings understand the words near, far, and no. After everything, which star is closest to Earth? The answer is still the Sun, and if the Sun is removed from the question, then the star closest to us is Proxima Centauri. But by the time this journey comes to an end, what matters most is no longer just those two names. More memorable than the names themselves is the lesson they force humanity to learn again from the beginning. In the universe, near does not mean reachable, and even the nearest neighbor can still lie beyond an emptiness that almost exceeds all human experience. Perhaps that is the deepest thing Proxima Centauri tells us. It does not exist to promise an early journey. It does not open an easy doorway out toward the stars. It simply stands there as a very real limit, forcing human beings to abandon their overly convenient ideas about distance. When even the nearest star beyond the Sun remains that far away, we begin to understand that the universe was not made to fit the scale of human intuition. And yet it is exactly at that point that knowledge begins to show its true value. Knowledge does not make distance disappear. It does not shorten the abyss between the stars through understanding alone. What it can do is more modest, but also more enduring. It makes that distance measurable, describable, and correctly understood. Every more precise measurement, every more patient observation, every more honest sentence about what we know and what we do not know becomes a real step forward for humanity in the face of the universe. And perhaps that is enough to close the opening question. The nearest star does not teach us how to reach it at once. It teaches us what distance really means, what a limit truly is, and why precision remains valuable even when it does not give comforting answers. In the vast darkness between the stars, understanding correctly is sometimes already a way of drawing closer.